So I'm Rémi Denis, and I happen to be, well, you don't really care, but I happen to be a software security research engineer. And this is not, I'm not talking about my work today. I also happen, and that's closer to this presentation, I also happen to be one of the main developers for the VLC media player, for those who know, sorry. And I have about 30 years experience in this industry. First let's talk to optimize programs, calculations. So when I started computing, I was still a kid and I was using my mother's computer. And back then, not working very well. It was running at 0.008 gigahertz. So it was pretty slow. But back then, it was nice how to make your program faster. You just waited a few years, got a new computer, and it was just faster. And in 2003, I got my first own computer at university, and it ran at 2.8, so several hundreds of times faster in just 10 years. But then something happened. We got close to the physical limits, and we couldn't increase clock frequency anymore, but instead we increased cores. So how to speed up the program? Well, obviously, first we tried increasing clock frequency. Then we used multiple threads, so there's symmetric multiprocessing and symmetric multithreading, which are kind of similar tech. The problem with those is you need to make your program multi-threaded, and that's notoriously difficult. And doesn't always work even. Or you can use specialized processing units like GPU, NPU, VPU, ISP, and so on. And then another trick that has been also used for general purpose computing is to use superscalar execution. And superscalar execution, is, well, you make your processor do multiple things at the same time in a single thread. And for instance, let's say that I want to calculate the sum and the difference of two values at the same time, so A0 and A1. Well, I will have those two instructions to run on the processor. They're independent instructions. I can run them if the processor is able to run them in parallel and save a lot of time by doing this without increasing the clock frequency. Of course, you need to increase the processor size. Now, the problem with this, you need to decode multiple instructions, and you have to look for dependency hazards or data hazards between the instructions, because, for instance, if you want to sum A0, A1, and A2, well, the second instruction depends on the first one. I can't run them in parallel, because if I would do that, then it would, obviously the calculations would be incorrect, because I need the result T0 of the first one to calculate the second one. So here comes vector processing, or sometimes also called SIMD or SIMD, for single instruction, multiple data. The idea is to apply the same instruction on multiple data elements at once. It's also called vector because, well, it's kind of like, you can think of it kind of like linear algebra if you've done first cycle math. And here, this was popularized in the 90s by Pentium MMX. And we basically tell the processor explicitly that we want to execute multiple calculations in parallel, and that it is safe to do so. Of course, it means we take the responsibility as a programmer to guarantee this to the processor to enable faster speeds. So today we're talking about this on RISC-V. So RISC-V, as many of you probably already know, means is a new instruction set architecture, which is an open standard with, in principle, royalty-free and no patent encumberment. And it means a reduced instruction set computer, which means that it's very easy to decode instructions for the processor. You don't waste. So your processor, you can dedicate it to calculating things and not to wasting time decoding the instructions, which would be the case on an Intel processor. And this also means that anyone can design their own processor. You don't need a patent license like for x86, or you don't need to buy a license expensively from ARM Limited, like on ARM. And you have vendors from China, US, Europe, and I don't know about Vietnam, but it might also be. So RVV, or RISC-V Vector Extension, is an open standard. There's already some open source designs for it, and there's also some real hardware. We'll come to that. It's also, the reason I'm talking about it is also it's a lot easier in 25 minutes to explain that than x86. And an interesting aspect compared to x86 especially is that it's scalable. So it basically write once, run anywhere. I think you've heard this story already in previous talks in this track today. So availability, there's currently one piece of hardware that's widely available, and it's actually quite cheap, so about 1.5 million dongs. but I think we're going to get, this is credit card size, we're going to get much better hardware within months or years. You can also emulate it on QEMU, of course. Just install the, on Linux, you can just install the binfmt QEMU wrapper, and it will literally run your RISC-V programs directly on your x86 or ARM Linux system. So this is really convenient for testing purpose. Anyway, that was the introduction. So let's have as simple as possible, still not that simple, but motivating example here. Obviously, in 25 minutes, we are not going to go through the 190 plus different instructions in the instruction set of the vector processing unit. But so the classic example for vector processing is SAXPY function, which means sum of ax plus, well, calculate a times x plus y. And this, well, if you know C, but even if you don't know C, is fairly easy. So what we do is we calculate the product of vector x by scalar value or constant value a, and then we add a vector y, and that gives us a vector. Obviously, this is a linear algebra. And this is a fairly simple example of how you can do vector processing because we are actually doing vector calculations here. I'm going to rewrite that function a little bit in a way that is more like the computer would actually want it, or the compiler would optimize it for you. And this is just essentially just removing the iterator and instead directly incrementing the pointer addresses as we go. It's actually faster to do it like that. And I mean, in practice, your compiler would do it for you, but this helps to understand what happens. So essentially, at each iteration of this loop, we decrement the number of elements that we still have to process, and well, we have to increment the 3 pointer addresses that we have as we go down the vectors. So one element by one element. But obviously, this is one element at a time. It's not very fast. So it in a way that is even more close to how the computer would actually see it, and we don't have while loops in computer. We only have conditional branches. So in practice, well, this is our main function. I've renamed the variables to use register names so that we can map it then to the code that's going to come on the next slide. So A3 is a count value. A0 is the first argument. It's target or output vector memory area. FA0 is a constant. It means floating argument number 0. A1 argument 1 is a second argument that is not a float, so it's the x pointer address here, and A2 is y, and then A3 is a counter. So this is what we would actually look like in more like pseudocode type of like how the compiler would probably implement this in practice. Of course, it's going to be in, with assembler instructions, but we'll get to that. And we of course have to have an explicit return at the end. So I don't know if many of you have done assembler before, but if you want to optimize it down to the instruction level, that's how it gets. For RISC-V, it's actually fairly simple. So instead of, now we are switching to assembler, so we're going to have to write this at the top of our source file instead of a .c. So we just say that, okay, first is .option arc is a directive for the assembler, which says that we are enabling the vector extension. Essentially, we are telling the assembler that, okay, it's okay to use vector instructions because I know my processor will have vector support. And likewise, we enable the ZBA. It doesn't matter much. And then we say .text. This means we are now writing code, which is text or the story for the computer, if you will. You could also write .data, then it would be like constant data or modifiable data, but text means that it's a computer program. And then we say we have a global function or global symbol, which we call SAXPY. And yes, there's no A here, it's how it is. It's not a typo in my slides, it's actually like that in the, and then we say, okay, SAXPY function starts here, and then we'll write our code. So after that, well, how do we put this? How do we put this in vector instructions? So if you have never seen assembler, this is going to look a little cryptic. Let's get through that step by step. So first, we have to tell the processor what is the vector length. So the number of elements that we have in our vectors. In this case, this was the count variable, which is now the A3 register. If you recall the previous slide. So here we tell it, well, we have A3 elements, whatever values that happens to be, and each element is 32-bit because we have float, and float is single precision floating point values in this example, so it's 32-bit per element. We could put 64 or 16 or 8 depending on the data. So if you want to do AI, for instance, it's going to be half precision, you could put 16-bit. You could say E16 to have 16-bit floating point calculations, for instance. And then, well, what we have here is so A1 and A2, X and Y vectors, they are pointers or addresses in memory. So the data is in the memory, it's not in the processor. So we need to move that data, transfer that data, or copy that data from the memory, the RAM, into the processor where it can make calculations. And this is called loading. So we do V for vector, L for load, and then E32 means element of 32-bit. And we say we load that address A1, and we load it into, we need to put, so the processor has 32 vector registers, named V0 to V31, not very original. And we need to pick one, like, it doesn't really matter as long as we remember which one contains what. So here I took 0, and this will load what was at address A1 into vector register 0. And then we do the same for Y, so from A2 into V8. So now we have we have copied the data of X and Y into the processor. We need to multiply X by constant A. And constant A is a parameter, so it's already in the processor, we don't need to load it. So we can directly do a multiplication. So this is V for vector, F for floating point. If you don't put F, it would be integer. Mul for, well, multiplication, obviously. Dot, and then we say what we are doing, what data we have input. So VF means one vector and one floating point value, or one scalar value, or one singular value, if you will. Here, for instance, the next one you have VV. This means we are operating with two vectors. And here VF means we have one vector and one scalar, or one singular value. So this calculates FA0 times V0 for each element in V0 and puts the results back into V0. So in assembler, usually you have the result on the second parameter, the first parameter. And then we do the add. So V8 plus V0 also into V0. This will add, well, this, which is X times A, with V8, which is Y. So we have our result. But now the result is in the processor, and we need to transfer it back into the memory, which, of course, where the calling code or the program expects it to be. So we need to do the opposite of a load, and the opposite of a load is a store. So vector, S for store, E32, because, again, we have 32-bit elements. Vector, and we say we are transferring the content of vector 0 into the address, the memory location or pointer A0. This kind of looks like this in C or in Rust or in like C++. All right, but there's a problem. So if we do this, the processor doesn't have infinite capacity to store infinitely large vectors. So if you have like 1 million vector and 1 million element in our vector, 1 million dimension vector linear algebra, this is just not going to work. So there's a trick here is that this T0 here, it will contain the number of elements that the processor is able to process at a time. And I mean, it's going to be more than one, but it's not going to be absolutely huge. We are going to have to iterate this set of instructions several times, and every time we will operate on T0 elements until we are down to until everything is calculated and we can exit the function. So in total, okay, it gets a little bit more compact here. So we again have our set vector length, then we count down. So A3 is the counter, so we just subtract. So we are going to process T0 element, so we can subtract T0 from A3 and update A3 and this. And here at the end, we check if A3 is not equal to 0, then we go back to 1. Then we have our load. So this is X, this is Y, this is the multiplication, this is the add, and this is the store. And here we have so this SH2 adds are just updating the pointers, so incrementing the pointers across loops. So the way this works is that actually, I think there might be it might be A1, T0, A1, but this adds so SH2 means shifted by 2 bits to the left. So this is shift a value by 2 bits to the left, multiply by 4 in other words, and then add it. So this calculates A1 equals A1, well, this updates to add 0 times 4. And the reason why we do T0 times 4 is that we have 32-bit elements, or 4 bytes elements, and in C, the compiler will do this adjustment, this multiplication for you, but in assembler, the pointers are always in byte values, so you have to adjust for the size of the elements you're operating with. Because if you think about how a pointer actually is represented in memory, if you've ever printed a pointer like in hexadecimal or something, you'll see that it's always in byte value. So we have to manually multiply by 4 because our elements are 4 bytes. Of course, if we had 2 bytes element because we would be doing AI stuff, then it would be times 2, and this would be SH1, because to multiply by 2, you have to shift by 1 bit to the left. And that's it. So at the end, we check if A3 is now down to 0, and if it is not equal to 0, then we go 1 to label 1. B means backward, so back up. We could put F for forward, but today, of course, it's backward. So yes, so that was the main hard part. Now we can rest our brain a little bit. And I mean, I know it's a little bit complicated. When it's around, it's actually much more complicated on other architectures. So let's go back to this set vector length instruction. So as I said, we have element size, 32-bit in this example. A3 is an input. It's telling we have this many elements available that I want to make my calculations with, and T0 is the output. Number of the processor tells us, the programmer, or conceptually, how many elements it can process in one iteration. And on current hardware, which I mentioned earlier, in practice, we have 128-bit vectors, so 32-bit elements, another 28-bit vector, we're going to get 4. I mean, of course, assuming that A3 is larger than 4, then we're going to get T0 is going to be equal to 4, which means we get a speed up of 4x times approximately. Of course, it depends on the hardware, but we can do better than this. And I mean, this is significant, but if you have a large scale, if you pay per minute of your VM runtime on some cloud service, increasing your performance by 4 times is actually a huge cost saving, but we can do much better than this. So there are additional parameters we can add here. M8, TA, MA. And M8 is officially called the group multiplier, but it's essentially an unroll factor, which I explain what it means. It's basically saying that, hey, if we go back to, you can, I have a URL to the slide, you don't need to go to take photos. Yeah, so if we go back to this, I'm only using V8 and V0 here, and I have 32 registers. I'm only using 2 out of them. That's kind of not very efficient use of my hardware here. So I'm like, well, I only need 2 vectors for this calculation. So how about I'll just pretend that I have fewer, bigger vectors. And the maximum you can use is 8. So what this means is that essentially V0 becomes a representation of all vectors from V0 to V7, so V1, 2, 3, 4, 5, 6, 7. V8 becomes 8, 9 to 15, and if we would use 16, it would be all the way to 33, and then 24 to 31. So by doing this, we end up having only 4 vectors, but they are 8 times larger than they would be if we had just used a normal M1. And this, again, improves the performance quite a bit. Like with this, we would typically get like 5x to 8x maybe. Perf, of course, it doesn't scale infinitely, but, and I mean, of course, we can use other values. So if we need more vectors, we have M4, M2, M1 is the default, and we can even go into fractional, so half, quarter, and eighth. TA means tail agnostic. It basically means that if we have less than 4 elements, if we have less than the maximum, we don't care what happens to the stuff after the end. So that's why it's called tail agnostic. The tail is the stuff. So if, say, you have a vector of 4 elements, capacity in your processor, and you have only 3 elements that you actually want to calculate with, you're saying that the 4th element at the end of the vector, I don't care what the CPU can do. It does with it. It can do calculations. It can ignore it, whatever. So essentially, you're telling the processor, please do whatever is fastest. For your implementation, I don't really care. And similarly, MA is mask agnostic mode. This is about masking. I'm not going to go into the detail of masking. If you're interested, you can read the specification. But again, it's another way of saying that don't need to worry about masking in this calculation. You can do whatever you want, whatever is fastest. So this, and that's pretty much it. So, and we're on time. References, well, obviously I only add, so we only have like 5 instructions. In reality, a vector instruction set is about 190, give or take, different instructions. I mean, you have subtraction, division, well, you don't have division, but you have all sorts of integer addition, like XOR and OR and 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 add and sub and reverse sub and whatever, and even more complex things like min, like which A plus B divided by 2. So I can't go through all of them. If you're, of course, in real case, if you want to take this into use, you're going to have to go through the RISC V Vector extension specification, which has all the list of all the instructions, and they are nicely grouped into different families, like integer, float, mixed with, and all sorts of things. The unprivileged ISA specification is a baseline RISC-V instruction set for like doing the base things like sub and branching, for instance. Again, I mean, you might need another condition, branch condition here. This is just an example. You can go to the unprivileged ISA specification for that. What's nice to note is that they have separate specifications for unprivileged and privileged. And if you're just writing like software, normal software, you can just use the unprivileged. Privileged is if you want to write kernel code or hypervisor code, which does the memory management, that sort of thing. So if you here, we don't care about that. So we have half of the specification that we don't need to care about. And then you have the ABI spec. That's where it tells you, that's a spec that tells you like which, how to like, where your parameter and your return values are going into the, which register or which, where they are going and how the data is laid out in your memory. It's essentially mapping the C and C++ and Rust and other D and well, all this native compiled language, how they map to the processor on this specific architecture. And you have ABI specifications on every architecture. There's an ARM ABI, there's even ARM 64-bit ABI, 32-bit ABI, x86, so there's a RISC-V ABI. And you can find all of these on the RISC-V GitHub. The slides are there, so if you need to take one screenshot, it's if you need to take one photo, it's this one. And also full working sources with the makefile and stuff there, and that's it. Yes?
How much was the vector instruction set in RISC-V compared to the Intel or AMD?
So in my experience, obviously it depends a lot on the implementation, and because RISC-V is an open specification and not a hardware as such, it will depend on the vendor. So this hardware I have, which is currently the main available hardware coming from, well, it's Canaan, but it's really made by T-Head, which is a subsidiary of Alibaba. I think for this loop, it gives us between, well, maybe 6 to 8 times faster, but it depends on the loop. And compared to x86 or ARMs, I think compared to ARM, it's roughly the same, typically. Of course, it depends what processor you have. Usually, you can't choose. Yeah, so x86 is AMD and Intel. So for x86, it's a bit different because x86 usually, on the face of it, using MMX, no, well, not MMX, but SSE or AVX will give you better improvements than this. But the reason I think is more like on Intel, the CPU is really slow for like non-vector calculations, for scalar calculations, because of the complexity. Because of the complex instruction set, they have to do a lot of work in decoding and like pipeline, like speculative execution, all sorts of things. And because of this, their scalar execution mode is actually quite slow. And because of this, they get a lot more benefit from vector calculations than a simpler RISC architecture like ARM or RISC-V. And for this reason, I think this is one of the reasons why you will see that AVX is actually giving you better performance compared to like plain x86 than RISC-V vectors would give you compared to RISC-V, and also if you compare like ARM Neon or ARM SVE to plain ARM. Yes.
You mentioned the E series RISC-V. So you mean the hardware is just is a better hardware from this year? It's just the hardware from your company or the hardware?
So I don't make hardware. I'm a software engineer. But I mean, I think this year several vendors have announced that they will release hardware. But the problem when they announce is you never know, did they make sense and then make hardware with, which then means that you have 1 or 2 years to wait before the CPU comes, or does that mean that they actually have a board that's coming, like that you can buy and order on immediately? So currently this one is available. It has been available since October last year. And if you order it today, you'll get it in a week. But there will be better hardware from a variety of companies. So you have T-Head Alibaba in China, and also Star 5. In US, you have Sci5 and Tentorrent, I think. And well, there's a whole bunch of them. Because it's an open ecosystem, there's a lot of competition.
When is the V series released?
So the vector specification version 1.0 was released 2.5 years ago.
2.5 years?
Yeah, approximately.
So right now we are
They're not touching the base spec. They're adding encryption extensions to improve the speed of also encryption algorithms, and maybe some stuff for AI. I don't actually know what they're adding. Yes? How many or what? So this hardware there, it has one vector-capable core and one non-vector-capable core. So it has 2 cores, only one of which have vector support. But again, there are some cores, there are some boards already available with 4 cores or 8 cores, and somebody has even made like a supercalculator with like I think 1,000 cores. RISC-V is just an instruction set, so you can do designs of whatever you want. I don't think there's a fundamental difference between, in terms of how many cores you can make, it doesn't really matter which instruction set you have. You can make them really large, you can make them really small. RISC-V scales up and down. And as I said, like of course, if you have multiple sockets, you could have really a lot of CPU and once there is one such hardware. I don't remember the name, I think Milk V something. Some Chinese company has made some really hardware with a really lot of cores, but they don't have this yet. So it's gonna take a few more years to get high performance vector cores, I think. So currently, obviously at that price, you're not gonna get a supercalculator. So this is good for early testing and benchmarking, but I think in a matter of year or two, we're gonna get really performant, like more like server class or mobile phone class type of cores coming. But I mean, I'm not a vendor, so I can't really. And if that's all, then I guess I'll release everyone for lunch.